Hello, welcome students. I am Rekha Thorat, Associate Professor. Today we discuss on comparison test for positive term series. Let us consider comparison test first type first. If summation of un and summation vn are two positive term series and k is not equal to 0, a fixed positive real number, and there exists a positive integer m such that un is less than or equal to k into vn for all n greater than or equal to m, then first result is summation of un is convergent if summation of vn is convergent, and second result is summation vn is divergent if summation of un is divergent. That means here in this comparison test, summation of un and summation of vn are two positive term series. Here k is not equal to 0, is positive real number. Then there exists a positive integer m such that un is less than or equal to vn, k into vn. un is less than or equal to k into vn for all n greater than or equal to m. Then first result is the series summation un is convergent if this series on the right hand side, that is summation vn, is convergent. And second result is if series on the RHS side, that is summation vn, is divergent if summation of un series on the LHS side, that is summation un, is divergent. Let us consider the proof of this result. Let Sn equal to u1 plus u2 plus u3 plus up to un, addition of first m term, sequence of partial sums, and Tn equal to v1 plus v2 plus v3 plus dash 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 plus up to vn for all n greater than or equal to m. Sn minus Sm equal to um plus 1 plus um plus 2 plus up to un, which is less than or equal to k into bracket vm plus 1 plus vm plus 2 plus dash 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 plus up to vn, as Sn is less than, as un is less than or equal to vn. Hence Sn minus Sm is less than or equal to k into bracket Tn minus Tm. Hence Sn is less than or equal to Sm plus k into Tn minus Tm. Hence Sn is less than or equal to Sm plus k into bracket Tn minus Tm. Hence Sn is less than or equal to k into Tn plus Sm minus k into Tm. Hence Sn is less than or equal to k into Tn plus n, where n equal to Sm minus k into Tm. Consider first case. If summation Vn is convergent, then sequence Tn of its partial sum is bounded above. Hence Tn is less than m for some positive integer as it is bounded above. Hence Sn is less than or equal to k into m plus n for n greater than or equal to m. Hence sequence, which is sequence of partial sum, is bounded above. Hence by theorem summation of un is convergent. That means if sequence of partial sum is bounded above, then given series is convergent, that is summation un is convergent. Now we consider another case. If summation of un is divergent, then the sequence Sn of its partial sum is not bounded above. That means Sn is greater than m for some large number m and for n greater than or equal to n naught. Sn is less than or equal to k into Tn plus n. Hence, Tn is greater than Sn minus n upon k, which is greater than m minus h upon k. K is not equal to 0. Hence, sequence Tn is not bounded above as it is greater than this number. Hence, summation of Vn is divergent. That means if summation of Un is divergent, then summation of Vn is divergent. And first case is if summation of Vn is convergent, then the less series summation of Un is convergent. Thus, if Un and Vn are two series, positive term series, and k is not equal to 0 is positive real number, and then for m, positive integer m such that Un is less than or equal to k into Vn. Summation Un is convergent if summation Vn is convergent, and summation Vn is divergent if summation Un is divergent. We get this result. Now we consider limit form of comparison test. That is theorem number 6. If summation of Un and summation of Vn are two positive term series such that limit of Un upon Vn as n tends to infinity equal to L, where L is non-zero finite number, then the two series converge or diverge together. That means here Un and summation Vn are two positive term series, and limit of Un upon Vn as n tends to infinity equal to L. L is non-zero finite number. Then the two series converge or diverge together. We have to prove this result. Since summation of Un and summation of Vn are positive term series, we have for L greater than 0, this implies L minus epsilon is greater than 0 for epsilon greater than 0. Now limit n tends to infinity, Un upon Vn equal to L. Hence, by definition of limit, there exists a positive integer m such that modulus of Un upon Vn minus L is less than epsilon for all n greater than equal to m. This is by definition of limit. Hence, L minus epsilon is less than Un upon Vn is less than L plus epsilon for all n greater than equal to m. We denote this result as number 1. From 1, if summation Vn is convergent, then summation Un is convergent, and as Un is greater than n minus epsilon into Vn for all n greater than or equal to m. Hence, if summation Vn is divergent, then summation Un is also divergent series. Hence, the two series behaves alike. That means from 1, if summation of Un is convergent, that means if summation Vn is convergent, then summation Un is convergent as Un is greater than n minus epsilon into Vn. Vn is convergent, Un is greater than L minus epsilon into Vn. So, if Vn is convergent, then Un is also convergent. And if Vn is divergent, then the greater series also divergent. That is, summation Un is also divergent series. Hence, the two series behaves alike. Now we consider comparison test of second type in the form of theorem 7. Statement of this theorem is, if summation Un and summation Vn are two positive term series and there exists a positive number m such that Un upon Un plus 1 is greater than or equal to Vn upon Vn plus 1 for n greater than or equal to m, then first result is summation Vn is convergent, then summation un is also convergent. That is, if the series summation Vn is convergent, then the series summation un is also convergent. And second result is, if the series summation un is divergent, then the series summation Vn is also divergent. That is, both the series behaves alike. In the proof, we write sequence of partial sum Sn equal to addition of first n terms of both the series, Tn equal to addition of first n terms. So Sn equal to u1 plus u2 plus u3 plus dash 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 plus up to un, and Tn equal to v1 plus v2 plus v3 plus dash 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 plus up to vn. For n greater than or equal to m, un upon vm equal to um upon um plus 1 into um plus 1 upon um plus 2 into dash dash dash, last term is un minus 1 upon un. Hence um upon un is greater than or equal to vn upon vm plus 1 into vm plus 1 upon vm plus 2 dash 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 vn upon vn minus 1 upon vn. So um upon um equal to vm upon vn. Um upon un equal to vm upon vn. Hence um upon un is greater than or equal to vm upon vn. Hence um into vn upon vm is greater than or equal to un. That is, un is less than or equal to um into vn upon vm. That is, um upon vm into vn, since m is positive integer. Un is less than or equal to k into vn for all n greater than or equal to m. Hence, summation un is less than or equal to k, which is less than or equal to vn. This shows that summation vn is convergent, then summation un is also convergent. And if summation un is divergent, then summation of vn is also divergent. Now we consider one example, that is some examples. State the behavior of the series. First example, summation 1 upon 3 raised to n. The series summation 1 upon 3 raised to n is a geometric series with common ratio 1 by 3, which is less than 1. Since the series is of the type 1 upon 3 1 plus 1 upon 3 plus 1 upon 3 square plus dash dash dash, and here the common ratio is 1/3, which is less than 1. Hence it is, by the result, geometric series convergent if the ratio is less than 1. Hence it is convergent. Second example is the series 1 plus half plus 1 upon 2 square plus 1 upon 2 cube plus dash dash dash, infinite terms. We write the given series in the solution. It is a geometric series with common ratio half, which is also less than 1. Hence, by result of geometric series, if common ratio is less than 1, then the given series is convergent. Next series, summation of 2 raised to n. It is also geometric series of the type 1 plus 2 plus 2 square plus 2 raised to 3 plus dash dash dash. Hence, here common ratio is 2, which is greater than 1, and by the result that geometric series is divergent for common ratio greater than 1, the series is divergent series. Next example is summation of 5 by 4 raised to n. We write the given series in the solution. This is also summation 5 by 4 raised to n is a geometric series with common ratio 5 by 4, which is greater than 1, and if in geometric series common ratio is greater than 1, then the series is divergent. So the given series summation of 5 by 4 raised to n is a divergent series. Thank you.